So first we will discuss what is the background and motivation for approximate computing, and in the next presentation, we will actually discuss the approximate computing techniques. So I would say, in especially for optimizing artificial intelligence algorithms, it's very, very important to know where we can approximate so that we just spend the right amount of effort. These are some of the acronyms we will use. So first of all, let us understand what is approximate computing. So in many scenarios, in many use cases, what happens is that if you want to do exact computation, it requires high amount of resources. Okay. However, if you can allow selective approximation or occasional violation of specification, it provides disproportionate gains in efficiency. So it will look like little too difficult term, but so what happens? See, suppose if you want to meet 100% cases, right? Suppose like if you are a doctor, right? And if people come to your clinic 24 hours of the day. So one option is you stay awake all the 24 hours, you don't go to sleep, you will be able to handle all the patients. But you know that, okay, it's not that all the time, even though your clinic is 24/7, but it's not that all the time patients will come with uniform frequency, right? Patients will come probably more during the daytime. Once in a while, you will have some patients in the night. So what you can do, probably you can stay awake during the daytime when the patients usually come, and other time you can take some rest. And if the patients come, they may have to wait a bit, but you can still serve them. So the whole point is, instead of staying up the whole 24 hours, which makes your life infeasible, right? If you can stay for the time that you can selectively approximate, that means selected customers or selected your patients, they may have to tolerate some amount of delay, but others can be served properly. Occasionally, it may happen some patient may have to go back because they may find that, okay, the delay is too much. So that means some of the requests may not be satisfied. For example, if you are like a data center, which is trying to provide, resources to a website. Now, what happens is that whenever there is some special activity, like for example, a political activity or a religious activity or a sports activity, so obviously the corresponding websites will get a lot of accesses, right? A lot of people will visit those websites. So during that time, suddenly you have huge amount of requests. At other times, you don't have so many requests, but during that time, you have huge amount of requests. For example, like we see some e-commerce website. Now they know that during Deepavali time or New Year's time or Christmas time, they will have huge amount of purchase requests. So during that time, some of the requests may be dropped. So of course, they still try to keep extra resources for that time. But the point is, selectively, if they allow one or two requests to be dropped, it allows other requests.
Sir, there's an interruption in your audio, sir.
Sorry?
So voice is not audible.
Voice is, how about now?
Yes, sir. Right now it's fine.
There is some noise, sir.
Please mute yourself, then the noise will go. Okay, so now if noise still comes, you please let me know. Okay. So the whole point is approximate computing exploits the gap between level of accuracy required by the applications and that provided by the computing system. That means the applications or users do not need that much accuracy. Your computing system may be providing you too much accuracy, but you don't need that much accuracy. So if you can exploit the gap between the level of accuracy that you need and that which is provided by the system, you can do some additional optimization. I will give you some examples that will become more clear. So approximate computing seeks to build acceptable or good enough systems out of unreliable or inaccurate hardware and software. That means instead of making perfect system, we just make acceptable systems. So here is an example. For example, if you see LXNet, so if you store the LXNet unmodified, it requires 233 megabyte of model size. If you want that, if you are okay with 1% or less than 1% accuracy drop, the model size that you need to store is just 99 megabytes. If you allow less than 10% accuracy drop, then memory needs of LXNet becomes just 32 megabytes. Okay, so from 233 megabytes, the memory model size comes down to 32 megabyte, although the accuracy is also dropped. If this drop in accuracy is acceptable to you, then you can have this trade-off. Similarly, in k-means clustering, if you can allow 5% accuracy loss, you can get 50 times energy saving. Okay, so what it means, for example, for 5% of points, they may not have reached their centroids. You can stop early, but 5% of the points may not have reached their centroid. So then you can get 50 times energy saving. Similarly, there is a inverse kinematics application. If you can do neural network approximation of it, you can improve the performance by 26 times for only 5% loss in the quality of result. I will discuss what is neural network approximation, but if we can do that, then we can get 26 times speed up for just 5% loss in quality of result. So usually what happens is that we have always heard that energy and performance, they are at odds with each other. That means if you want to get higher performance from this point, if you want to get higher performance, you have to spend a lot of energy. Although you don't get much performance, but you have to keep on spending a lot of energy. And if you want to go to lower energy, that means if you want to save energy, you have to lose performance. So here, we are in approximate computing, we are adding another dimension, that is error. So here, from this point to this point, as you can see, we have better performance, we have lower energy, both. That means without losing performance, we are having energy efficiency. We are having better performance, lower energy consumption, but at the cost of non-zero error or some amount of higher error. Okay, so that is the whole idea of approximate computing. And similarly, we can have many frontiers. You can have different degrees of trade-off between performance, energy, and error. So there are some terms which are used for approximate computing, like dynamic effort scaling, quality programmability, variable accuracy. Now, in any application, there will be some portions which are approximable, whereas some other portions are not approximable. So portions which are approximable, they are called soft slices of computations or best effort computations. That means for these computations, it's okay to just make best effort. We can't guarantee 100% accuracy for them, but we can just make best effort. They are non-crucial or non-critical, error-free, or sorry, error-tolerant, error-acceptable, tunable, having forgiving nature, and so on. So these are some of the words you will find out in research literature. So you may doubt actually where is the scope for approximate computing. We have all till now dealt with exact or precise computing. So where is the scope for approximate computing? So sometimes there is inherent scope for approximate computing. Sometimes approximate computing is unavoidable. You have to use approximate computing. For example, let us take first this example. So here you can see that these are the different definitions, high definitions, FHD, WQHD, UHD in 2015. So here you can see the amount of pixel data that you need is more than 25 megabytes. Now, how to process all the data, how to store the data, storing the data takes too much amount of storage, right? So in such scenarios, we have to do compression or even lossy compression just to save that data, because if you want to store it, it takes huge amount of storage, and you may not even need that much precise video. Okay. Similarly, sometimes the input is noisy. If input is noisy, so what it means? That means the data that you're getting itself has errors. So now, even if you do exact computing on it, you don't get much benefit. If the input itself has some errors, then even if you compute it exactly, anyway, your output still will have some noise. Similarly, you have limited data precision, like floating point data, hardware defect, right? Suppose if your hardware defect is there, that means the hardware sensor you're using will be capturing the data with some defect, or the computing unit that you are using, that will have some defect. You may get sudden additional load, as I give the example of this website, right? Suppose there is a sports event or religious event or political event and so on. So those websites will have sudden additional loads. So in those cases, it always happens that you will see during those times some of your orders could get skipped or have some mistake, because it is beyond anybody. Sudden additional load, it's not designed to handle that much load. Or sometimes there are hard real-time constraints. So you have to meet the deadline. So that means, okay, drop everything else and meet the deadline. So when you drop everything else, means some approximation will be there. Okay, so in those scenarios, you have to use approximate computing. Similarly now, so for example, like here, if you have, for example, 100 tasks, right? So here you have to meet the deadline. Each of those tasks must get finished within 1 nanosecond. Okay. So this latency cannot be increased, right? This is the maximum latency which can be tolerated. Although each of the tasks may get finished with poor accuracy. Sometimes you have to lose the accuracy, but the latency wise we can't tolerate. We can't compromise. We can't have more than 1 nanosecond latency. So that's why in those scenarios, that's an example of hard real time. That means you have to meet the deadline. Something like, like a railway crossing has to be closed. When before the rail comes, it has to close. No matter what happens, it's a life threat on someone's life. So that's an example of a hard real time constraint example. So in those scenarios, you have to drop something else and do this. Similarly, in search engine, there is no unique answer, but many answers are acceptable. So for example, if you have a search result in front of you, suppose you have 1, 2, 3, 4, 5, 6, 7, 8, some 10 results. So as long as the answer you are looking for is in top 3, right? Suppose if it is top 3, it doesn't matter whether it is number 1, number 2, or number 3. As long as it is within top 3, it's okay for us. So there you can do the computing approximately. That means as long as it is within a certain range of top numbers, maybe top 3 or top 5, it is acceptable to the user. Similarly, in algorithms, I'm sure you might have at least heard of many problems for which an exact solution is not even known, but some heuristics are known. Right? So those are the example of approximate algorithms. So approximate algorithm is efficient and sufficient. Then second motivation is that many times programs are highly resilient to the errors. For example, humans have some perceptual limitations because of which we can't distinguish more than certain thing, right? For example, if peak signal to noise ratio, PSNR means peak signal to noise ratio, if it is more than 30 decibel, it is considered acceptable. So now, once it is more than 30 decibel, now whether it is 35 or 45 or 65, it doesn't matter. All we need is above 30. So instead of making this 65, why not reduce it to 35, so that you don't have to spend as much effort to bring it to above 65. You can just keep it just above 30, maybe like 32 or 35. And that will save a lot of your resources, lot of your efforts will be saved if you don't go to much high PSN. Similarly, as you know, if in front of our eyes, if we see more than 30 frames per second, we can't distinguish more than, it will look to us like a video, right? Similarly, humans can hear only between 20 hertz to 20 kilohertz frequency. So like this, so we have a lot of limitations, and these limitations allow approximate computing, because anyway, at the end, if you give me some number, like suppose you ask me what is the value of pi, I tell you 3.14151619 and so on, so forth. You give me the number after till 1 billion digits after decimal. Anyway, I'm going to say all this, I will probably just use 3.14. Right? I will just use 3.14. That's my limit. I can't do much mathematics. I can't do mental math like a supercomputer. So anyway, I'm going to throw all the numbers after second digit of decimal. So why give me so many numbers? Just give me 3.14, or maybe like just 22/7. So I can maybe cut this with some other number, right? So this is the example of how humans have limitations. So there is no point of unnecessarily collecting, more digits after decimal. Similarly, in many applications, there are non-critical portions. That means they can be easily approximated. For example, in 3D ray tracer, 98% floating point operations are approximable. Similarly, clustering, for example, K-means clustering, only relative distances matter, not absolute distances. For example, if you want to find out whether a particular point, whether it belongs to this centroid or this centroid, all you need to see is to which centroid is it closer. Exact distance does not matter. It just matters whether it is closer to this centroid or to that centroid. So all that matters is relative distances. Absolute distance doesn't matter. Similarly, in document analysis, processing of common words such as A of D can be avoided, and you can see it yourself. You can, in Google search engine, you can try to give some queries with these words A of D and without these words. Your answer will be usually same, because these are insignificant, okay, unimportant words. Similarly, now there is redundancy due to spatial and temporal correlation. So here I've shown average percent of differences between adjacent pixels in 10 images. So here, that means you take an image, then find out that for one pixel, how many of the nearby pixel values are similar to that pixel. So more than 75% of pixels are less than 10% different from their neighbors. That means most of the pixels are almost similar to their neighbors. Okay, so here that means most around 75% of the pixels are less than 10% different from their neighbors. That means most of the pixels are similar. For example, if you see my background like here, or if you see the sky, this pixel is probably same as this pixel. So nearby pixels almost usually have similar. So, but instead of processing all the pixels, we can just process some of the pixels and their values will be similar. So that is the example of spatial correlation. And temporal correlation means, for example, if there is a slow motion video, right? If there is a slow motion video, then one frame will have very similar, pixel values as the next frame. Only after multiple frames, the person will change. For example, if I'm trying to move, right, very slowly, very slowly, I'm trying to walk or move, you will see that in many frames, my position in the picture is almost same. My posture is same. Of course, if it is a fast motion video, right, then in every frame there's a lot of change. Okay. Now, error resilience of programs. And another example is like in iterative refinement algorithms. You can run extra iterations with reduced precision of intermediate computations, and you can still get the same QOR. Just 1 minute, I have to slide this. Okay, so yeah, I was discussing how in iterative refinement algorithms. So here is an example of iterative refinement algorithm, like Newton-Raphson method. So you might have actually seen those type of algorithms. So here you start with initial estimate x0, then you apply some function, and then you get a better estimate x1, and then again you make x1, you put it back here, then you get x2, and so on. So each iteration you get a closer value of root. So here, running extra iteration with reduced precision, you can get still QRs, same QR. For example, two options. One option is you run it with FP32, and probably you have to run for suppose 55 iterations. Another is you run with FP16 instead of 55. Now you have to run probably 80 iterations. So you have to run extra iterations, but because you're using reduced precision, but now you have to run extra iterations. But the benefit is that on FPGA, right, on FPGA, this approach allows greater parallelism for a fixed area constraint. Because greater parallelism, why? Because instead of 32-bit precision, now you're working with 16-bit precision, right? So that's why you can have twice the instances. You can have two instances simultaneously running on the same FPGA, right? You can have, suppose one, this is your FPGA. You can have one part which is running FP16 and another is FP16, and both of them are running, right? And this one is taking 80 iterations, this is taking 80 iterations, but totally effectively, if you say, because you are running twice the iteration, effective iteration is just 40. So compared to 55, you are having now only effectively 40 iterations. If you just compare. So the whole point is, in this way, this iterative refinement algorithm, they are usually error tolerant, because if you work with less accurate, precision, then less accurate values, you may have to do extra iterations. And if it is hardware like FPGA, you can have greater parallelism for a fixed area constraint. So here is an example. I'm trying to include, especially in this approximate computing presentation, I have included a lot of examples so that you can immediately get a feel of what it is. So here is an example of that. We are doing k-means clustering. Okay, so on purpose, that means purposefully, we are trying to inject errors in the cluster centroid. Okay, so here, this is the clustering quality impact if we don't inject any error, the green one. Now, even if we inject up to 1% error, that means this yellow bar, then it has this yellow thing is non-different from the green. This yellow line is non-different. You cannot distinguish it from the green line here, right? You can see the yellow and green, they overlap. That means even up to 1% error has no impact on the quality of clustering. Okay. Similarly here, this is the accuracy of SVM classification, support vector machine. So previous example was k-means clustering. Now this example is support vector machine classification for handwritten digit recognition. Here error is injected in one randomly chosen bit out of 15 LSB. So that means only one LSB is chosen out of 15. It's not that all the 15 LSB, they are injecting error. Only one LSB out of any of the last 15, that means 15 LSBs they choose and inject an error on them. Injecting an error means they flip the bit. If it was originally 0, they make it 1. If it was 1, they make it 0. So you can see the blue line, the classification accuracy is not impacted. So no impact on accuracy as long as the error is injected in one of the 15 LSBs. And here is the error probability. This left side is we inject the error with very less probability, and right side is error is injected with a probability of 1. That means definitely we inject the error. So here you can see that as long as the error is injected in one of the 15 LSBs, there is no impact on the accuracy. So till this point, is it clear to everyone, or do you have any questions? Okay, if you have no question, let us go forward. So now till now we have
Hello,
discussed. Yes, please.
Sir, I have joined late, so sir, I am not able to understand LSB. Sir, what is LSB?
LSB is least significant bit.
And sir, these 19-bit, 15-bit, what these are output bits?
No. Okay, these are not output bits. These are, I think, actually in this figure it is not specified. So usually, I think these are the variables which are used in this SVM, support vector machine classification. So you take those variables and with some probability you inject an error in one of the last 15 bits or last 19 bits.
Okay, sir.
Okay, and then you find out what is the classification accuracy of digit 0, right? Hand digit recognition means you have to recognize whether it is digit 0 to digit 9, one of those 10 digits, using support vector machine algorithm. I'm sure you will study about this algorithm in your machine learning course.
Hello, sir.
Yes.
Sir, how to find error in 15 bits?
No.
If any bit corrupted?
No, that's not the way. See, it's called a fault injection technique. So you read it here. Error is injected in one randomly chosen bit out of 15 LSBs. That means, see, original, suppose the correct value is some value, right? Suppose 0, 1, 1, some 1, 0, some combination, right?
Yes, sir.
Now you choose, suppose these are the last 15 bits or whatever number of bits these are. So you choose one of them randomly. Suppose you choose this bit. And if it was 0, you flip it to 1. If it was 1, you flip it to 0. That's all. That's the meaning of error injection.
Sir, what is the purpose of error injection?
We are trying to see how error tolerant this algorithm is.
Then if any bit is corrupted, then how we correct it?
We don't correct it, right?
How we detect it? If any bit
No, we don't have to detect it. We are purposely correct. We are purposely, corrupting it.
Okay, sir.
Right? We are purposely corrupting. We are purposely introducing an error to try to see how error tolerant this algorithm is.
Sir, why we don't use K means K clustering?
No. Try to understand. Unnecessarily don't ask question. K-means clustering is a different algorithm. This is a different algorithm. We are trying to see error tolerance of each algorithm separately. And here I'm giving some examples. I'm not trying to give all the examples. Some examples I've chosen.
Okay, sir. Thank you, sir.
Okay, now what are the other reasons why we use approximate computing? So we can do efficiency optimization and we can have quality configurability. So approximate computing can improve performance and energy by relaxing the accuracy. So that means, as I already explained, approximate computing allows you to improve performance and save energy. For example, in DRAM, and DRAM requires refresh operations. So we can reduce the DRAM refresh rate, or we can reduce the SM supply voltage, which reduces the memory energy. So SRAM usually, supply voltage could be like 1 or 1.2. So if you can bring down the supply voltage from suppose 1.2 volts to 0.6 or 0.7 volts, your operational power is saved, right? It takes less amount of power. Now, approximate computing can alleviate scalability bottleneck. I will give an example of this later. It can allow early loop termination. I will give an example. It can allow us to skip memory accesses. This should be obvious, because if we are not doing certain computations, we don't need to fetch data from memory for those computations, those values, right? Or if we are, suppose, instead of 32-bit data, we are only fetching 16-bit data, then we can also reduce memory accesses. And how can approximate computing improve yield? So can anybody answer? Sagar, can you answer? How can anybody think? How can approximate computing improve yield? I hope you know what is yield, right? Suppose you are producing certain, chips. The yield means how many of those chips are good chips. If whichever is bad, they are thrown away. Whichever are good, they are kept. So suppose out of 100 chips that you design, suppose 40 are good, then your yield is 40%. Now, how can it improve yield? Anybody can answer?
Sir, because we are having energy saving through is approximate computing. Sir. We are getting
Okay.
we are doing energy saving, so we are not bothering about much energy, much error, and we are focusing on to
No,
reduce
how can
the
it improve
energy.
yield? How it improves yield? Yield is something I'm asking. How can this? Your answer is not very precise. It's not still correct. Anybody else? So yield means how many chips are correct.
Hello.
Yes.
Hello, sir. I am Aditya.
Yes. Yes.
In approximating computing, we are not concerned with too much accuracy, so we will have to input less power, and performance is improving. So we are getting more output as we required by giving less input. So yield is improved.
No. That's not correct. So see, yield means what is the yield means how many of the chips are functionally correct. Okay. So suppose what happens actually is that suppose you want to design a CPU which where your target frequency is 2.7 gigahertz. So and each stage should have a proper correct proper latency. It should not have more than a certain latency and so on. So now whichever chips don't meet those criteria, they will be thrown away. Similarly, you will see that each cell should be able to store suppose whatever is the memory portion, each memory cell should be able to store the data reliably. If it cannot store the data reliably, it will be thrown away. Right? So now with approximate computing, you can even work with partially functioning chips, because some of those portions, some of the memory cells may not be working properly, but you can still use them. Right? Because you don't have to throw them. They will give some small error. That's all. I can live with it. That's what approximate computing allows. That is something I spoke on slide number 1. Let me go back to it. It's not one. Slide number 3. This slide, the first slide. We just want to build good enough system. I don't want to build pakka or perfect systems. I just want to build good enough systems, which are acceptable, not necessarily perfect. So that's how my yield could be improved. That means some of the chips which I was earlier discarding, I can now still use them. Under precise computing paradigm, I can't accept them, but under approximate computing paradigm, I can accept them. Okay, so is it clear?
Yes, sir.
Okay. Now another thing is that approximate computing provides knob to trade off quality with efficiency. So I will give an example of this later. Okay. So what is a knob? What is a knob? Like my fan has a knob, right? So I can increase the speed of the fan, or I can reduce the speed of the fan. Oh, hopefully, I mean, it may be false, but I hope when the speed is very, very high, the fan is giving me a lot of air, but it is also consuming probably more power, right? And when the fan is at very, very low speed, then fan is not consuming much power and it is not giving me much air. So that's the meaning of a knob. So that's why the more quality we want, the poor efficiency it will be. That means the energy efficiency will be poor. That means you have to spend more energy, and vice versa. So that's the meaning of knob. That means we spend only as much effort as required by the QR requirement. For example, we can write program versions of different quality. One program may be using int variables. Another program may be using float variables. Another program may be using double variables. Each of them may give different quality of a result, but that's fine. Here's an example of what I was saying is that how it provides knobs to trade-off quality with efficiency. So here, PSNR loss due to error in a single bit at various positions. So previously we were doing it last 15 bit, last 19, 28, and so on. Here, this is the output image which you get after certain image processing algorithm if you allow error in the LSB, that means the last bit. Here, this is the error you get if you allow error in bit 3, starting with bit index starting with 0. If you insert an error in the fourth or fourth least significant bit, and this is the image you get. You get almost noisy image. You can't see anything. If you insert an error in the most significant bit. So I hope now everybody can understand that here, as long as I insert an error in either this bit or this bit or this bit, the overall error quality is easily tolerable, right? If you see the PSNR, I already told you that PSNR values above 30 are considered acceptable. So usually here I'm getting PSNR above 30. So now if I were to, here they have not shown what is the image quality on if you insert an error in this bit, but at least till we insert bit error in this bit, my PSNR value remains above 30. Okay. So I hope this point is clear. This LSB to MSB, I'm sure everybody might have heard about it. What is MSB?
Sir,
Yes.
we are changing, means we have a error at a single bit, na? Like
single
in the
bit,
first case.
yes, single bit.
So,
yes.
sir, how it is the quality is so degraded at the MSB means?
Okay, so suppose you have an 8-bit number. Okay, so number is suppose 0 1 1 0 1 1 1 1. Right? Suppose this is your number.
Yes, sir.
Okay. So what is the decimal equivalent of it? This is 96 plus 15. Okay, this is
yes.
This is 111. Okay.
Yes,
this number is actually 111. Now you flip it. You flip this bit. So what this number becomes? It becomes 1 1 1 0 1 1 1 1. So what is the decimal equivalent of it?
Plus 220 255.
What you say?
We have to
suppose
add
this is unsigned. Suppose this is unsigned number. Okay.
Yes,
so what is the decimal equivalent of this number?
That's 100.
239.
239, right? 239.
Yes.
Okay. So from 111 it became 239. So much change. But if I were to insert an error in LSB, what does this number become? 0 1 1 0 1 1 1 0. Right? What is the decimal equivalent of it? 110. Right? So now can you see the difference?
Okay, sir.
From 101, this number can either become 100 or 239. So which will have larger error? Tell me now.
Yes, got it.
This will have larger error, right? Here the error is very, very small. Error that we are inserting is very small error.
Sir, what is PSNR?
PSNR is peak signal to noise ratio. Signal to noise ratio. That means how much signal is there, how much noise is there.
So what it tells?
Sorry?
What it tells? I mean, what it conveys? PSNR.
It tells the quality of the image. Actually, there are. I will give you an exercise to find out the PSNR value for certain image. You will yourself be able to have a feel of it. So the more the PSNR value is, the better the signal is, or better the image is.
Okay.
Okay. So here is another example. So suppose you have this function, right? x1, x2, x3, or x inverse, or sine x, or log x, or and so on, or root or square root of x. Now you train a neural network to mimic this function. Okay, and now that neural network can either have zero layers, zero nodes in the hidden layer or 5 nodes in the hidden layer, right? It has suppose one hidden layer, and now that hidden layer can have either zero neurons, that means there is no hidden layer, or 5 nodes or 10 nodes or 15, 20 or 25 nodes. Now, depending on how many nodes you have in the hidden layer, the percentage error in this overall neural approximation is reduced, right? From going from 0 to 25. If you don't have any node in the hidden layer, that means if you don't have any hidden layer, the error is very, very large, 22.8%. But here, even with just five nodes, the error goes down to 1.1%. Here it goes down to 0.68% and so on. Similarly, if you want to do square root of x, if you don't have any hidden layer, the error is 13.7%. Here it is 1.9% and so on. So the whole point is, as you have more and more complex neural network, your error in approximation is reduced. Of course, one more thing you can observe is that probably you can just stop at 10. After going to 10, you get very marginal return. You don't get much return, right? Do you agree with me or not? Anybody who doesn't agree, please let me know. That means from 0 to 10, there is very good decline in the error, 0 to 10. But after 10, there is not much decrease in the error. That means it is now already reasonably accurate. Okay, and sometimes there could be even fluctuations, right? Here, error has even increased. So that's why, that means there is overfitting. So that's why we can stop at this point. Okay, so in this way, we can see that how many number of nodes we should have in the hidden layer, so that the error in the approximation is reduced. So how do we do that? That you don't have to worry. I'm just trying to explain you. I'm trying to motivate how there is a huge scope for approximation in almost entire machine learning or deep learning that's happening. Okay, so now what are the challenges in doing approximate computing? Yes.
Sir, how we will decide, sir, how many nodes are useful, sir?
Yeah, so one thing you have to see is how much error is introduced. That's what I showed. Another thing is for different number of nodes, you will have different hardware costs. Right? Your circuit will become correspondingly more complex or less complex. So that based on all these consideration, you have to decide. Suppose your whatever. Suppose your boss says, okay, I can't tolerate more than this error. Okay, so if I can't tolerate this, then you have to use, suppose you have sin x function, and the boss says, okay, I can't tolerate more than let us take an example of this square root of x, that is easier to understand. Suppose he says that I can't tolerate more than 1% error. So you have to use at least 15. No, sorry, no, not 15. You have to use at least 20 nodes. If you need to bring the error to less than 1%, you have to use 20 nodes. Even if it is very costly to implement, but you have to use, because there is an error that the threshold should not be exceeded. Okay, is it clear?
Yes, sir.
Okay. Now, as you can expect, approximate computing is not an ultimate solution. It has certain limitations. So many approximations hold in a limited range only. For example, approximating sine function using a neural network, you can't do it in unbounded range. You can only do it in a bounded range. So here is an example that, for example, you have this function y equals to 1 by x. You approximate it with this function. So this function will give you here. So see here there is, if you see, as you can expect, this thing cannot be true for the unbounded range. It can only be true within certain range. That means within this range, 0.5 to 1, this function is mimicking this function. Similarly, if you want to compute square root of 1 by x, sorry, 1 by square root of x, then instead of actually computing it, you can just do this linear equation. which is again true only in this range, plus it will have some limited amount of error also. Similarly, log x, it will have certain error, right? And so on. So here, here is an example, like instead of this precise function, we are using imprecise or approximate function, and that will have its limit, and that will be valid only in a certain range. I just wanted to highlight that your approximations may be valid only for a certain range. It may not be always valid. And some applications cannot be approximated. For example, cryptography. You may not know cryptography, that's fine. But at least one property of cryptography, I'm sure everybody may know, is that so here, for example, there is a plain text. This plain text is all 0, and this plain text is all 0 except this number. So that means this plain text and this plain text is different by just 1 bit. Now you supply this key. Okay, this is the key is saved to both the plain text, and now the cipher text, that means the crypted text, that has 65 bits different. This is the property of cryptography, that is called avalanche effect. Avalanche effect means even small changes in the input or small changes in the key will have very drastic impact on the output. So now here you can't approximate, right? You can't say, okay, I just changed 1 bit, because here some huge number of bits will change in the output. So cryptography has to, like your key, if your password may be like very long, but it can't tolerate even one mistake. Your password has to be exact only. Can somebody hack your system with a approximate password, right? Approximate password means your system is hacked. That's why password can never be allowed to be inexact. Password has to be exact. Similarly, correctness issues will come up. If you try to approximate control flow, then program will not terminate. It will be an unsolvable equation, or it will lead to a crash. And approximate computing technique will lead to corrupt output, which may be undetectable by a quality metric. So, for example, if you try to do compression, right? So after compression, suppose originally the size was 1 megabyte. After compression, the size is 0.2 megabyte. So it may be that you just see, okay, the size is what I expected, but it could be lossy compression. It could be compressed in a way that you cannot recover it. So size does not give you an idea whether the compression was done correctly or not. Right? Size does not show whether the compression was done correctly or not, whether some information was lost or not. So approximate computing may interfere with synchronization and memory ordering, and it may lead to non-deterministic output. So that means every time you run approximate computing, your output will be different, will come out to be different. The approximate computing technique is same, but because it is causing non-deterministic execution, the output every time comes out to be different. Now these errors are very difficult to debug, right? Anybody who has done any type of debugging of any program, they know that at least you expect that error behavior to be repeatable. Only then you can do debugging. So, and avoiding it is lot of overhead, I can tell you. That's why you have to use approximate computing with lot of caution. You may have to compare it with single-threaded exact execution, because parallelism introduces its own challenges. Actually, I'm not going into parallel computing here. I will introduce very briefly parallel computing later on. But once you find an error, sometimes even debuggers can't help you fully. Okay, so now I will tell you example of how approximate computing errors are very difficult to debug. So here is a code. Okay, can anybody tell me what does this code print?
Uh, 0.43.
Very good. Anybody else? Anyone else?
Sir, 0.43.
Okay. So it doesn't exactly point print 0.43, it prints this number. So now it's very, very difficult to debug, right? Why? To reason why. So I will discuss float, double, and int later on, and fixed point numbers. Then you will get some idea why this kind of strange behavior. So unless you know the full picture, it becomes very, very difficult to debug these things. So the reason is 0.43 is not exactly representable using float. What if you change it from float to double? Now what happens? Can anybody tell me? That means instead of this float, I change it to double.
So maybe then it can show the correct result because the range of double is higher than the float.
Yes, yeah. So then it will correctly print double. Yeah, 0.43 because in double you can represent 0.43 exactly.
Yes.
So you could never expect that because this number you stored it, and at least when you print it, this same number should come back, right? So these are some of the issues which come up when you use approximate computing. So floating use this float number itself is a approximate number. We are doing approximate storage of the number. So that's why these issues are coming. Okay, so now can anybody tell me about this number? We have float p equals to 23.42 and double q equals to 23.42. I check whether this number is equal, whether p equals to q. So does it print 1, which means true, or does it print 0, which means false?
So false.
Okay, I think
Why?
So because float produce less than 23.42 and then it will be wrong.
Okay, what about this?
Again false.
Anybody else? Please mute yourself. Please mute yourself. Yeah, anybody else?
True.
Why?
True, sir. True.
Why?
Because sir, it is already a integer value.
It's a whole number.
And
Yeah, actually, more specifically, it is power of 2. So it is exactly representative. So 23.42 is not stored exactly in float, whereas 64 is stored exactly. The error in storing 23.42 is different in float and double. That means a different approximation of 23.42 is stored in float and double. Hence, they are unequal. Okay, whereas a correct representation of 64 is stored either in float or double or integers. That's why they will come out to be equal. Usually, actually, equality operation is not defined on this float and double. So you should never use this equality operation on float values or double values. You will always usually get strange answers. You know, these operations, more than or less than, these are defined, but equality operations will usually lead to some strange output in float and double. So you should never use them. Okay, now this is a very big check for you. Let us see if anybody can crack it. Float x equals to 0.1. If x equals to 0.1, then print if. If no, then print else if. Else print this. Now you tell me what is the output of this. Anyone? Else. Any other guess?
Sir, else if.
Sir, if
So someone says if. Someone says else if. Why someone says else if? And why someone says else?
Sir, because I think ये 0.1 f function take one digit after point and approximate it, and it is representing float, I think.
So why not this? This is also one digit after decimal, right? What is the difference between this and this then? So I think all of you are guessing. You don't know the exact answer. Actually, the output that will print is else if. So when you see this float x equals 2 point, suppose you print this float x equals 2.1, and then you try to print size of x. So because x is float, it will print 4. Size of 0.1. 0.1 actually, unless you specify f, it will be stored as a double. That's why it will print 8. That means 8 bytes. That means 64 bit. So this 0.1 is actually, in fact, it's not a float. It is a double. So values used in an expression are considered as double unless a f is specified at the end. So 0.1 is not exactly representable by float, and that's why if you compare this 0.1 with this 0.1, because this is float and this is double, that's why they will have a different errors, and that's why they are not comparable. Okay, so I'm sure.
Sir, what is 0.1 f? Why we have written 0.1 f?
F means it is a float. We are specifically storing it as a float, not as a double. Unless we write f, it will be stored as a double.
Okay.
Okay. So last example for today. I think I will discuss it next time. So we are already on time.